Hi everyone, my name is Chi-Ying. I'm from University of Illinois at Urbana-Champaign. The title of this presentation is Hurricane Wind Damage Risk Assessment for Residential Buildings in the U.S. Southeast Coast in Changing Climate by Using Artificial Neural Networks. So this is our outline. I will talk about why we want to do this study, and then I will briefly introduce what other people have found and what's the next we want to do. Then I will introduce the basic concept of artificial neural network and how to use NARCS for time series prediction for predicting non-stationary hurricane parameters. I will also talk about how we improve the network prediction performance. And finally is the hurricane parameters forecasting result and loss estimation result. So this is a US catastrophe losses by perils, and as you can see that tropical cyclones make up a large portion of total loss. And this is a sea surface temperature or SST projection by IPCC. The global SST is expected to increase in the future. And this is a time history of the number of loss events. You can also see an increasing trend in meteorological related events. It is believed that the increasing of SST can fuel up hurricane intensity. So we would like to know the future hurricane risk under climate change. Existing studies about hurricane hazards usually are about hurricane intensity and frequency, and it is believed that hurricane intensity will increase in changing climate conditions. However, on the other hand, there's no consensus on whether the frequency of hurricane will increase or not. But some studies show there is more high-intensity hurricanes than we ever had. Most of the existing studies on hurricane loss prediction show climate change will cause higher loss in hurricane damage. But most of existing studies either focus on relatively smaller regions or use linear regression for predicting non-stationary hurricanes. So in this study, we will use statistical tools to establish a surrogate model to predict hurricane parameters for conducting hurricane simulation. We also like to investigate the difference in the extent of climate change impact to different regions in the United States. So this is our approach. The hurricane parameters can be categorized to time invariant and time variant parts. We will use variable selection to identify climate variable that can be used as the input to predict time variant hurricane parameters. Then from the IPCC projected global SST, we can use the NARCS to predict the future selected climate variables. And once the relation between climate variables and the hurricane parameter is found, we can use NARCS to predict the future hurricane parameters. On the other hand, for time-invariant hurricane parameters, we can use historical observation to conduct distribution fitting. Then the fitted distribution together with predicted time-variant hurricane parameters, we can build the distribution model for hurricane simulation. Then we conduct hurricane simulation and put the simulated hurricanes to hazards multiple hazard to do the loss estimation. The hazards multiple hazard is a risk assessment tool developed by FEMA. I would like to introduce the basic idea of the artificial neural network. In artificial neural network, we have several input variables and several target variables. Then we will use a hidden layer or several hidden layers that contains several hidden nodes to connect input and target. We will have pre-assigned weights for each link to decide the strength of each link. Then the input information move forward. We can get the error between prediction and target. The error will be propagated backward to adjust the weight. So after iteration of this process, the network then finishes training and can be used for prediction. So this is a feed-forward backpropagation neural networks. To conduct time series prediction, we need to use NARCS. NARCS stands for Nonlinear Autoregressive Network with External Input. So besides usual autoregressive time series prediction, it can consider other input variables as well. In our case, the Y is the hurricane parameters we want to predict, and X is the climate variables we use to help the prediction. So to train a network, at the beginning we have X and Y. we will go through a tap delay line that decides how many previous steps we will use in the prediction. Then similarly, all inputs will have a weight and bias. They will be summed up in a hidden node and go through a transfer function to generate a response. The bias decides whether the transfer function will be activated or not. Finally, we can get a prediction and we get the error to adjust the neural network weight and bias. So the training process is in an open loop. After training, we can close the loop for prediction. The final outcome of the open loop will be the initial condition of the closed loop. In the closed loop, we use predicted output as input for the next step. In this process, we have several ways we can use to increase the prediction accuracy, include use selected climate variables, and change the hidden layer structure. That includes the number of hidden layer and number of hidden nodes. We can also use different feedback delay, and we can try different transfer function, and we can try use different training algorithm. So we can have many different network configuration to try. To improve the network performance and decide the network configuration, we use network ensemble technique. This is the time history we want to use to train the NARC neural network. We first divide the data to train and testing set. So we can train the NARC network and get a prediction result. Then we can conduct this process many times, and each time we will get a prediction result, and we can give each prediction a weight that is based on the prediction mean square errors. Using this weight and these NARC network functions, we can get the prediction of the test data. Then we can use the performance from the test data to choose the best network configuration. Then I will introduce the climate variables. Climate variable we use are relative humidity and sea surface temperature from 6 basins. And also we consider the SST difference between basins. Under each variables, we can derive their temporal and spatial average, minimum, and maximum. So totally we have 110 climate variables. For variable selection, we use 3 approaches. The first one is very simple, straightforward approach. We use R² of 1-to-1 linear regression result of the hurricane parameters to each climate variables to decide which variables to be included. And second is the RKK information criterion, AIC. The AIC comprises 2 parts, regression performance and the penalty. We want to minimize the AIC, so we try to find the subset of variable that has the better regression result with fewer predictors. Then third is elastic net regression. This is the objective function we want to minimize. It also comprises performance term and penalty term. The penalty term includes the regression coefficient we want to estimate. During the model tuning process, the elastic net will shrink those coefficients and some of them will be shrinked to 0, so we can achieve the purpose of variable selection. Then I will talk about the time variant hurricane parameters we want to predict. First is annual mean of central pressure difference. We can find its distribution. In this study, we will simulate high intensity and normal hurricanes separately so we can further fit 2 distributions for them. After we use NARC neural network to predict the CPD, we can find the increment of CPD mean value relative to no climate change conditions. This is a CPD mean value increment. It will be used to apply to both high-intensity hurricane and normal-intensity hurricane CPD distribution to get the shifted one under climate change. The second time-variant hurricane parameter we consider called RMH. It is the ratio of number of major hurricanes to the number of total hurricanes. The hurricane frequency remains the same as in the no climate change scenario, but the number of high-intensity hurricanes out of simulated hurricane will change. Finally, we are using climate variables to predict hurricane parameters. Since we have 110 climate variables and we only use annual data from year 1944 to 2016, so we have to pre-select variables or the regression problem will be underdetermined. So first we group the candidates. For example, we can group all tropical Atlantic SST and tropical RH together. Then we can conduct linear regression starting from the global SST to hurricane parameters, and the selection is based on the linear regression result. Then we can get the selected candidate group. Then we can construct the first NARCS model for predicting selected candidate group from global SST. So this process is a pre-selection process. Then using the selected candidate group, we go through 3 variable selection methods, and each of them go through 96 NARCS setups, 288 network configurations to be selected. We select the best one with the best ensemble model prediction. Eventually, we can use the global SST to predict the selected climate variables and then to predict the hurricane parameters. So this is a validation of ensemble network models. So the gray lines are a result of individual networks and the blue line is the ensemble one. We can see it can capture the general trend very well. We want to know the climate change impact to hurricane loss of residential buildings in the US Southeast coastal region. In each study region, hurricanes are simulated at the coastline and the loss are calculated within each study region. Florida includes 2 cases. One is hurricane making landfall on Atlantic coast and the other is on the Gulf of Mexico coast. The hurricane parameters used for hurricane simulation are derived based on regions by using historical data. The table is 10 invariant hurricane parameters. We have the annual occurrence rate, approach angle, CPD for non-major hurricane and for major hurricanes, translation wind speed, and filling rate constant. From the 10 invariant CPD, we use the projected increment of CPD mean value to get the shifted CPD distribution. And from annual occurrence rate, we use the projected RMH to get the number of higher intensity hurricane and normal intensity hurricanes. We use the IPCC projected global SST to forecast 10 variant hurricane parameters, CPD and RMH. This is a forecasting result. We would like to know the change for near-term and long-term projection under climate change. So subtract the CPD mean value from no climate change condition, we can get the mean value of CPD increment over 120% from near-term to long-term projection, and the RMH increase over 10% from near-term to long-term projection. So use the distribution model, we can simulate hurricanes. Since the loss estimation in hazards is quite time-consuming, we simulate hurricane using Latin hypercube sampling to reduce sample size. So this is a result. If we set $10 billion as a standard, the region with lowest and highest probability of existence are region 1 and region 2. And we can see the probability of existence of both these regions increase dramatically under climate change. Then it is the percentage increase of estimated loss of study regions. We can see Texas and Florida has highest percentage increase. And for Florida, climate change seems to have earlier impact on hurricanes making landfall on Atlantic coast than on Gulf of Mexico coast. We propose a framework of hurricane loss estimation under climate change, and we also validate a NARCS neural network for predicting hurricane parameters. And for Texas and Florida, 2 of the most hurricane-prone states in the United States may have higher hurricane risk in the future. These results are based on the worst climate change scenario, and we are not using this result to terrify people. Instead, we hope people, especially the government, pay more attention to the climate change issues. Thanks for watching this video. This is my contact information. Any suggestions are welcome. See you!